All right, how's it going? I have got PA2 from most people. If you did not submit or did not add me as a reporter and I wasn't able to download it, I sent you an email a little after 8 o'clock this morning. So if you got such an email from me, it also asks you to please take care of this, and if you're not sure how, come and talk to me. So I had hours this morning at 8, I've got hours from 12 to 12:30, and I'm teaching from 2 to 4 and 126, but you can probably find me in there with some spare time between about 2:15 and 3:15. So come by, and if I'm not like talking in front of the class, which I probably won't be, I can help you with Git at that time also. So make sure we touch base and we get that worked out. Let's talk about the current ODP. So ODP 213, due tomorrow morning at 8, you're implementing a hash function, okay? And it's not the same hash function you're going to use for PA3, it's a different function. But it's the same idea. It's a function that takes a string and returns an integer. It's just called hash, takes a char star, and returns an int. And for this hash function, the algorithm is just add up the ASCII code of every character and then reduce modulo 31. So you just do a %31, and you should get a number between 0 and 30 inclusive. So some sample hashes, if you hash the letter A, it's one character, ASCII code 65, divide by 31, the remainder is 3, your hash function should give you back a 3. If you hash ABC, you should get 12. If you hash uppercase hello, you should get 0. If you hash hello with lowercase letters, you'll get a different value because the ASCII code for lowercase e is different from an uppercase e. So there's some samples you can try. And I have a note here. When you want to test this, you've got your hash function. You can call it by just saying hash quote HELLO. And that should return an integer, and if you print that out, it should be the value that you see here. If you hash hello with lowercase letters, it should give you back a 4, and so on. But if you do something like an fgets, right, so let's say you have a string array, and you say fgets, string array size standard in, and then you say hash temp, and you print out the value of I, right? If you type in HELLO and hit enter, and then run that through hash, you're not going to get a 0. Because when you type something in with fgets, it throws a new line at the end, this extra \n. So here, you're hashing a string with 5 characters, HELLO. If you call fgets and you type HELLO and hit enter, the string you're passing to hash is 6 characters, HELLO, followed by character 10, that new line. And so when you add up the ASCII codes, you're adding in an extra 10, your hash is going to come back with a value of 10 instead of 0. So that doesn't affect your ODP because you're not ingesting a string, you're just writing the hash function. And you just go through and just add up the characters. And if you call hash and the last character is a new line, just add that ASCII code. There's no special treatment for any of this. This is only an exception if you're writing your own main program to test your hash function. And if you write your main program to take a string using fgets, just be aware that whatever string you type in, that's not the string you're passing to hash. You're passing that string plus a new line at the end. And that can throw off your tests. But don't do anything special in the hash function itself. Just loop through, add up the ASCII codes of all the characters, reduce modulo 31. Is that clear?
I was just worried about that during the programming time.
You do. So let's talk about that. So suppose you type in hello and you hit enter. Here's what your array looks like. This will be HELLO \n null terminator, and then who knows after that. Okay, if you want to get rid of that null terminator, all you got to do is, if you want to get rid of that new line, all you got to do is write a null terminator in that location. So what is that location? It's the location of the last character. So the last character of a string temp well, what's the index of the last character? HELLO, yeah.
String length minus 1.
String length -1. Right, HELLO \n, that has a string length of 6. The last character is at 5. ABC followed by a null terminator has a string length of 3. The last character is at index 2. A, B, C. So this is temp bracket string length of temp -1. So in general, if you have input from standard in using fgets, you know there's a new line at the end. If you want to get rid of that, you can do it as follows. All right, and that's something that you'll end up writing, 10,000 times in your life. But that changes this new line into a null terminator, which means that's where the string ends, which means your string is now just HELLO. If your last character is not a new line, this will still get rid of the last character. So don't do this unless what you really want to do is just get rid of whatever the last character is in your string, which if you're calling fgets, that's the new line. So in PA3, yeah, it says enter a license plate. You type in ABC-123, hit enter. The thing that fgets gives you back is ABC-123 with a new line at the end. And if you start hashing that, you're going to get different locations from what the test program does. So probably first thing you want to do is strip that off. Or scan with %s's or something like that. All right, any questions about that? So ODB 213, just write your hash.c. It's just a for loop. Go through every character in your string, add up the ASCII codes to a running sum. When you're done, sum equals sum %31, return sum. That's your whole function. And you're going to have a similar function in PA3, but the algorithm is more complex than just adding the ASCII code. It's the ASCII code times the position plus 5. And then you reduce modulo whatever the hash size is, which is whatever we tell it to be. Okay, so let's talk about Valgrind. So I'm writing some true junk code here, which will not do anything useful. I have a struct node declared. I'm going to make temp a struct node star. I'm going to malloc a size of struct node and set that equal to temp. And I'm going to set the data field equal to some number. And then we're going to have a loop which says, well, temp next is not null. Do some stuff. And at the end, we're just going to exit. Okay, so so I don't want memory leaks, so I'm going to free my node that I malloced in the beginning at the end. And so this should run without memory leaks, and it won't do anything, right? But it should compile. And I can run it, and it looks fine. Okay, if we val grind this, and I run it, yeah, it tells me heap summary at the end, all blocks were freed, no leaks are possible. But we got this message up here. Conditional jump remove depends on uninitialized values. Okay, this is a problem. It's warning you that there's something going on with memory that you're not quite doing right. And we want to make sure we don't get messages like that. Even though it's not a memory leak, even though your program may look like it runs correctly, there's still a problem. Okay. Now PA2 I'm not taking off for those. I'm taking off 5 points for memory leaks, but I'm not taking off for these warning messages that pop up. I will for PA3 and forward those. So let's talk about these. Conditional jump remove depends on uninitialized values. That's really what's going on here. You're using a memory location that you have not specifically given a value to. And that's always dangerous. Now a lot of times if we don't give a value to a memory location, it turns out to be 0, but not always. And it may always happen on one machine, but not on another machine. And so you write code on your Mac and it works perfectly, and 7:30 in the morning, you push it over to GitLab, and just to check, you go onto the server and you pull it back down and you run it, and it seg faults. And you got like 25 minutes to like figure out what's going on, right? Because on a Mac, certain things are initialized in certain ways, which is different from how it's done on our Linux server, right? Well, if you're using Valgrind, which somebody has gotten to work on their Mac, by the way, if you're using Valgrind, right, and you're seeing things like this, it's warning you that could happen. Okay, there's something going on. So one thing you can do, compile with a G switch, and then run with Valgrind. And now it's telling me main.c line 13, there's something going on with an uninitialized value. So that helps me localize where the problem might be. Let's go into main.c, bless you. Let's go down to line 13, which is right here. And it says, while temp arrow next is not equal to null. Well, the only variable here is temp arrow next. That must be uninitialized. It's apparently null because we didn't print anything. But why is it null? Well, because it happened to be null, not because we ever said temp arrow next equals null. So we initialized the value of the data field in the Sentinel, but we never initialized the value of this field. That's what Valgrind has noticed and is warning you about. So how do we fix that? Right? We want to make sure if this is a Sentinel node for an empty list that the next field of that Sentinel points to null. That's how we know that it's an empty list. And then when we add something, it'll point to that something. So if we do that, and we run this, now we get a really nice, clean, succinct output message. Right? Heap summary, nothing in use, everything was freed, no leaks are possible. That's what you're after. All right, so here's a snippet of main program that I've seen people write. So we have a temporary character array, and we're going to check to see if the first character of that input is an X, which means exit. And if it is, then we're going to exit. Otherwise, we're going to do some stuff like print hi and get the next line of input. And we'll say goodbye at the end here. And this works fine. I can say hello, cool, and I can say X, and it exits out. So that works fine, right? But if we run this on Valgrind, there's another warning saying conditional jump remove depends on initialized values. And this time it's calling line 6 in main2.c. I compiled with the G switch up there because I knew it was going to happen. So line 6 in my main program is using an uninitialized value. So let's go into main 2, let's go down to line 6, and it says, well, buffer bracket 0 is not equal to x. Well, why is buffer bracket 0 uninitialized? Because nothing has ever assigned a value to it. It was just declared in the previous instruction to be a character array, but character arrays aren't initialized. There's a small chance that randomly, when I run this the first time through, buffer bracket 0 might be x. And my program would exit without ever asking for input. And if you run your program and 20 times it seems to work fine except for this valgrind, but once in a while you run it and it just exits for no reason at all, right? That's a hint that there's something not initialized.
So could we just set buffer 0 equal to null character?
So you could set buffer 0 equal to something other than x, null character would be fine, or the usual way that this is done is read into the buffer before you check to see if the person said x. And so you'll see this structure a lot. You do something outside the loop, and then you do it again at the bottom of the loop. And the idea is you want this thing, whatever it is, to happen each time you get to the top of the loop.
Also like a do-while loop?
Or you can do a do while,
Oh, those are pretty
right?
much-
Or sometimes you can squeeze two statements together, right? It's hard to do with buffer bracket 0. But fgets also returns the address of buffer. So you could probably say, well, fgets bracket 0. I don't know if that will work or not. But we can try that. Right, so now it's not complaining. I don't think this will work. Wow, a line of code I've never written before. Whoa. Oh, that was weird. Oh. Yeah, this does work. So we get rid of this at the bottom. Yeah. All right. I don't know how other teachers would feel about that. That would raise some eyebrows, but I think that's pretty dang cool. Right? So if you look at the manual page for fgets loads into that buffer, but it also returns the address of that buffer. Right? And if we have an address of a character array, we can say bracket 0. So that works. That would be a cool bonus question on an exam. All right. So valgrind, play with it. If you're having trouble figuring out where your valgrind messages are coming from, like come by and we'll run through your code. But compile with -G, and that should give you at least some information. May not be exactly where the problem is. Okay, but it'll at least point you probably to the right variable to look at.
You can also use, there's a option. for
Switch.
that.
Yeah. Which one is it?
So I think I saw pop up, it was dash track, I think dash origins is equal to yes.
Track origins equals yes.
Yeah.
Increases the size of the basic block translations. Okay. Oh, cool. Okay.
Basically the same thing.
Yeah. Cool. So there's all these switches you can turn on in valgrind to get more information and greater verbosity of messages and such. So that sounds like a useful one. -- track origins equals yes. And there's like a few options. All right, any other questions, comments? So let's talk more about PA3 and hashing. So PA2, I'll get through a bunch of them today, but I teach till 4, so I don't have a lot of time after that. But almost definitely by the end of tomorrow, I should have all the PA2s graded if they were turned in this morning, and then I'll start on the next batch. But I've graded a few of them so far, and they look good. Right, memory leaks, not a big deal. And other than that, they look like they're working well. If you don't have great confidence in your PA2, right? You know, I've got an annoying habit of finding little problems with code, right? I'm not worried about those. But if your code is seg faulting consistently, or it's not compiling, or you add something and it doesn't appear when you say print, right? You kind of know if your PA2 is basically working or not, right? If you feel like it's not working, or it's not working well or reliably, right? Definitely come talk to me as soon as possible, okay? Catch me in office hours, or catch me after class, or shoot me an email or something, and let's nail it down. Because you got to use lists for PA3, and we got to use this arrow notation, dereferencing, malloc freeze, all of this stuff for everything else we're going to do. So definitely come and talk with me, and we'll figure out what's going on. So PA3, meanwhile, all right, we're making a hash table. Hash table is an array of sentinel nodes. Okay. So we have the following pieces. So we know what a node is, right? It's like a linked list node, but instead of an integer, it's got 3 strings. Character star plate, first name, last name, and then it's got a pointer to the next struct node. So right, that's a single linked list node. It turns out this is also what we have in our hash table. So our hash table is an array of pointers to sentinel nodes. So I've suggested a type def in the assignment that we call a struct node star a hash entry. It's also what we called an LL, or a list, or a mylist, or something like that for PA2. But it's a pointer to a struct node. And that's what each of these things are. It's a pointer to a struct node. And I want to start loosening the terminology a little. Not only because it's easier to talk about, but because it helps to sort of think about this thing differently. What is actually in the hash table is a pointer. It's a memory address. And what does it point to? It actually points to a sentinel node. But it actually points to a struct node. But what it really points to is the first byte of the first field inside a struct node. Okay, if we really think about this in terms of like legalese, if a struct node is this thing that starts with a character star plate, then a pointer to a struct node is really the address of the beginning of that pointer to a character. And we want to know that, but we don't want to dwell on it, right? And it can get even worse. It's actually the address of the first byte of the address of the first character of the license plate in that first node, right? But there's a different way to think about this. The extreme other end of that line of thought is, this is a linked list, this is a linked list, this is a linked list, this is a linked list. We can actually think of this table as just an array of linked lists. And logically, that should make some sense to us. in terms of the actual mechanics, that's kind of silly. We don't actually have, you know, a chain of 100 nodes sitting in this one entry in this hash table, right? This is just an array of pointers. But logically, we can think of this as just a linked list. And when we think of it that way, what we're going to do right now, which is writing out some pseudocode, is going to flow much more naturally. So I'll usually talk about this as either a pointer to a struct node, or a pointer to a sentinel, or I may sometimes actually call it a sentinel node, or I might even just call it a linked list. The linked list whose sentinel node is the struct node to which this points, or to whose first byte this points. Okay, so there's multiple terms going on here. They all are intended to mean the same thing. And if we can think of this as just, this is a list, it's a linked list, just like we've been doing in PA2, right? Then we can do some things fairly comfortably. All right, so let's talk about the init function first of all. So we want to implement a function called hash init. So this is a hash entry pointer. And it takes one argument, which is the length of our hash table that we want to create. So a hash entry star, that's an array of hash entries. That's our hash table. So we could define hash entry star, I don't know, let's just call it table. And we need to allocate this on the fly because we don't know ahead of time if it's 5 elements or 500 elements. So you're going to allocate it with a call to malloc. And how many bytes do we need for this array of hash entries? Well, it depends how many entries we want, and it depends how big a hash entry is. So this is, how many entries do we want? It's len. And how big is each entry? Well, we don't know, but the system knows. We can say size of, and what do we want the size of? A hash entry.
And that gives us one block in memory.
That gives us one contiguous block in memory, which can hold len hash entries. That's our array. So that's the first part. Allocate a chunk of memory to be our hash table. But if we run this with Valgrind, we're going to get a zillion messages about uninitialized values because we have not actually given any value to each of these locations in our array, to each of these hash entries. We've said this is, let's say len is 10, we've said this is 10 hash entries, but those are uninitialized values. This could be, you know, totally random values in here, and if we start trying to use those, we're going to segfault. So we need to initialize them. So set table bracket 0, that's the sentinel node of our first linked list. So set table bracket 0 to be a sentinel node for an empty list. Table bracket 0 to be a sentinel node for an empty linked list. And also bracket 1, bracket 2, all the way up to bracket length -1. So if length is 10, we have to create 10 sentinel nodes, each pointing to an empty linked list.
So would you then not need a sentinel node in the linked list itself?
That is the linked list, right? And so, I mean, you're going to create a linked list, and you're going to, remember, these things are actually pointers. So this is going to point to the sentinel that begins your linked list, right? But is that part of the linked list, or is it an entry in the table, or is it both? Point of view. Awesome question. Okay, this is one of these connections that is confusing at first, and even after you think you've got it, it comes back to being confusing sometimes. But this connection is vital, right, to being more comfortable with working with these dynamically allocated blocks. Okay, how do we set table 0 to be the sentinel node of an empty linked list? Well, we could say table bracket 0 equals malloc size of struct node, table bracket 0 arrow data equals 42, table bracket 0 arrow next equals null. Don't do that. That's way too much work. Okay, we have another way of getting a sentinel node to an empty linked list. It's called list init. Creates an empty list and returns a sentinel node. And you're going to take your functions from PA2, your list functions for initializing, adding, searching, freeing, and so on. You're going to rename them. You're going to let them take strings instead of an integer, right? But you're going to have all these functions in, list.c or some file like that. We can use these, right? So list init creates a sentinel node for an empty linked list. So how do we set table 0 to be such a sentinel node? We can do the following. Bam, you're done. Call your list init function. That will do the malloc. That will set the data field. That will set the next field. It will return the address of the sentinel. And hey, you just take that and you pop it into hash table bracket 0. Throw that in a for loop so that you do that for table 0, table 1, table 2, table up through len minus 1. And each time you do that, the value you store in your table will be different because list init always returns a new location in memory. So if len is 50, you're creating 50 sentinel nodes here. And they each function as an independent list. But in your hash init function, you don't have to worry about any of those details. You never have to call malloc. You just call your list init function. And when you're done, what do we return? Just return table.
So if we ended up doing PA2 like very well, can we just carry all of that over?
Absolutely. Yeah. Yeah, if you've done PA2, you've got a linked list package, you want to use that in PA3. And you need to make some changes. What are the changes? Well, number one, a change to the struct node. Okay, because your struct node is going to be this. So it has 3 data fields, plate first and last, and then a next field. So that's one change. 2, when you add something, you need to allocate space for the plate first name and last name. So in your add function for PA2, you could say new node arrow data equals number, right? Here it's going to be something a little more complex. You're going to have to use string copy new node arrow plate, comma, plate that I want to save. String copy new node arrow first, comma, first name I want to save, and so on. But before you can do that string copy, you got to allocate space for what you're trying to copy in, because these are just pointers. So the function of your add routine, the previous, current, moving through, and so on and so forth, none of that is affected by this. But also, I'm telling you to just add in the beginning of the list. So all the looping to find, compare if this is bigger than that or that, forget about that. Hack all of that out and just pretend that your list is empty. Just add right after the sentinel and point to wherever the sentinel was pointing. So you have to make some changes, but your function is simpler. Your list find, that's just your search function. But instead of searching to see if number is equal to node arrow number, see if string compare of plate, comma, node arrow plate, see if that string compare returns 0. Print, you have to print out the plate and the first name and the last name in that particular format instead of just printing the number. Free should be the same, right? Except you also have to free the dynamic memory you allocated for plate, first name, and last name. And then list length is a new function, but that's just going through, instead of printing, just add a counter and return how many nodes you counted. So the gory part of PA2 you can reuse completely.
Real quick about the list length one.
Mm-hmm.
So, what is it really tracking? I know it says data node, but it's all the nodes in the linked list.
Mm-hmm.
So, is that the plate, first name, last name?
That's one.
That's one.
That's one. So if your linked list looks like this, so you've got a sentinel, and it points to A, B, C, 1, 2, 3, and a first name and a last name, and that points to, X, Y, Z, 4, 5, 6, and a first name and a last name, and this is null, and you call list len with sent, it should return 2 nodes. If your list is empty and you call list len, it's just got a sentinel node, it should return 0. So it's how many actual license plates you've stored in your linked list. And so it's just like print. Instead of printing this, increment a counter. Instead of printing that, increment a counter. When you're done, return the counter. All right, so let's talk about our add function. So hash add, you pass it the hash table, you return hash table, license plate, first name and last name. It should add that to your hash. Well, again, we have our hash table. It's got a collection of linked lists, right? How do we know which linked list we want to add our license plate to?
The return value of the hash function?
Right, the return value of the hash function. So the one extra layer here, instead of just saying add this to your list, well, we have to know which of these 50 lists we want to add to. That's what this hash function is for. So hash is what I'm calling an actual function. It's what you're writing in ODP 213 with different details. It takes a string, it returns an integer. So when I talk about hashing a license plate, what I mean is take that license plate, pass it to this function, get an integer back. So we can talk about hashing a plate as in a verb.
Is this a pre-built function?
No, you have to write this, right? But it's like what you're doing in ODP 213, except 213 is just a straight sum of right, it's with this part removed. It's just a straight sum of all the ASCII codes, and it's always mod 31. For a general function, you multiply each ASCII code by the position plus 5, and then you reduce mod whatever the hash size is. Okay, which brings up one other detail on our init function. So this is a good hash init, right? Malloc table for malloc space for the array, loop through and set each array entry to be an empty linked list. Okay, and then return. The one detail is anytime that you use this hash function, anytime that you try to add something or search for something, or if you want to loop through and print the length of each linked list in your table, right? We need to know how big this array is, how many entries we have. And arrays in C, we can't know the length just from looking at the array. We've got to have it stored somewhere. And the only time that we ever talk about the length is right here when we call hash init. So this is the one place I'm going to let you use a global variable. Okay? If outside of your hash init function, you say integer hash length, and somewhere inside here I say something like hash length equals len, what that's going to do is take the value that you passed to your hash init, it's going to copy it up in here. And this value is available to any piece of code from this point on down in your file. So if this is all sitting inside hash.c, and I have hash length declared in the beginning of hash.c, all of my hash routines in here have access to this hash length. Okay, and you're allowed to do that.
You can just have that in your log. Could you just, from all the other functions, would they be able to see that variable?
Only if it was global. And I don't want you to do that. I don't want you to make this global in your main, outside your main program.
If the functions were in different files, would they still see the global variable?
If every hash function is in a separate file, that gets harder. I would say put all your hash functions in a hash.c, put all your list functions in a list.c, put your main program in a main.c. Okay, otherwise you have to get into a keyword called extern, and it starts getting more complicated. Okay, what I don't want you to do is this. Right? I don't want you to make this thing global to your main program and whatever else you put in here. Okay, because now if somebody buys your hash package and they want to be able to store things in a hash and search your hash and so on and so forth, you've got to tell them, oh, but by the way, in your main program, make sure you declare a global variable called exactly hash length outside, right? And that's just kind of goofy. Okay? If you have a global variable here inside this hash.c, you can compile this up, you can hand them the .o file, they never have to deal with this. This gets set by hash init, right? And it's sort of within here, and this is kind of where we're going to go in 223, where we're sort of bundling things together. So this I will let you get away with, although I think at WSU it still gets you a 0 on your assignment, because it's a global. But this definitely don't do, okay? Even for this class. But you can put it in your hash functions. And then if you're doing a hash add, first thing you have to do is hash your play to an integer. When you call your hash function, you can use hash length, right, inside your hash routine. How bad is what?
So other than setting the global variable, what would you do, and how bad is that?
The right way to do this is, instead of having a hash table be an array of hash entries, have it be a structure that includes an array of hash entries and includes an integer, which is the hash length, and maybe includes a flag saying it hasn't been initialized and all sorts of other stuff like that. And that's, yeah, I mean, that's a straightforward way to do it, and that's really what we do when we get to objects in 223. But particularly in C, where arrays have to be stars and so on and so forth, I felt like it would get more convoluted than I wanted to for 222 project 3. So we'll just do a global. Globals usually make your life easier until they don't. Okay, so let's write hash add. This is a void. It takes the following arguments. Takes a hash table, takes a license plate, takes a first name, and it takes a last name. And our goal is to add this information, license plate, first name, last name, to our hash, which means add it to a linked list. Well, which linked list do we add it to? Well, it depends what the license plate is. We're going to take the license plate, we're going to hash it, which means run it through our hash function. And the value we get back from that function, that tells us which linked list we want to store our data in. So we can do something like this. Right? Take your plate, run it through your hash function, gives you back an integer. If that integer is 5, then you want to store your data in the linked list, which is at table bracket 5. If it gives you back a 7, you want to store it at table bracket 7, at the linked list, which is at table bracket 7. Okay, table bracket loc is a sentinel node. Pointer to a sentinel node. But we think of it as a sentinel node. How do we?
So what is the hash function return?
Integer.
And what's the reason?
It's the result of that.
Oh, okay.
Right, so pass a character string, it gives you back an integer.
Oh, and that would be where.
That's where in the table.
Yeah.
Yeah. Yeah.
So it's how they had decide how to store them efficiently.
Yeah, it's instead of just having one big linked list where you have to search the whole thing, if we have 1,000 linked lists, then each one is 1,000th the size it would be otherwise. So it makes things more efficient. Okay, table bracket loc is a sentinel node of a linked list. How do we add something to the beginning of that list? Well, we could say, you know, new node equals malloc, and new node next equals table bracket loc arrow next, and table bracket loc arrow next equals new node, and new node arrow plate equals this and that and all this other stuff. Don't do that. Too much work. We don't have to do that because we have a function called list add. Takes a sentinel node, takes 3 strings, adds it to the beginning of the list. So your hash add function is really just this. List add. Table bracket loc, comma plate, first, last. There's your whole function. Okay, this is money, right? This is what you want to get to. This is code reuse, this is modularization. I don't care about mallocs, I don't care about arrow next, I don't care about null. I care about adding to this linked list these 3 pieces of information. Well, there's list add function, I'll just call it. So your hash add function is really simple. Your hash find, exactly the same thing. Call list find, table bracket hash plate, comma plate first last, and just return whatever that returns as your hash find value. One call, one statement. So think about that, okay? When you're working out pseudocode, think about your hash functions in terms of how can I use the power of my list functions, okay? And then you can code those up, and they're mostly just a few lines of code, and then you have to tweak your PA2 list functions into the list functions for PA3, and then everything should just go together. That's the theory. All right, so we'll run through some more pseudocode tomorrow. And we'll talk about questions with all of this, but that's basically how PA3 is going to feel. It's going to be a lot of reuse of what you've already done, bundling things up and using them. All right, so I will see you next time.